Welcome to the fascinating world of data structures. Friends, before starting with data structures and algorithms, let's see a real-life example. All of us know the famous Google search engine. Do you know how many pages the Google website contains? It consists of 16 billion pages. It means that when you search for a particular word, the search engine has to search from billions of words. Isn't it a very tedious job? But the search is completed within 0.1 millisecond. This is possible only with the help of efficient data structures and algorithms. So friends, for developing software of any real-world applications like media player, games, multimedia, stock analysis, browser, etc., we basically need to deal with some data and some processing on that data. These data are organized in various ways known as data structures, and the processing which is carried out on the data is known as algorithm. The data structures can organize the data items linearly, circularly, hierarchically, or in many ways. This leads to different types of data structures such as arrays, stacks, queues, linked lists, graphs, trees, hash tables, and so on. These data structures have their own algorithms like traversals, searching, and sorting. Nicholas Wirth once said, program equal to data structures plus algorithms. In your day-to-day computer usage, you might see that media player uses the queue data structure. The printer also uses queue, and the databases used in bank applications use the B tree as the data structure. So, various data structures are used in different software applications. Now let's see an interesting concept related to data structures. Complexity of program. The performance of a program can be analyzed by its complexity, that is, the amount of computer memory and time needed to run a program. So, we use two approaches to determine the performance of a program: space complexity and time complexity. Let's see what is space complexity. The space complexity of a program is the amount of memory it requires to execute. The program needs this amount of memory in some proportion. If this proportion is more, then the program is more complex in terms of space complexity. To represent the complexity of any program, we use a notation called as Big O notation. For example, consider one-dimensional array. As it is linear, its space complexity is O of n. As you can see, the complexity is represented using function of n. Likewise, if space complexity is quadratic, then it is O of n square. If it is cubic, then O of n cube, and so on and so forth. Now let's see what is time complexity. The time complexity of a program is the amount of computer time it needs to execute. Let's try and calculate the time complexity. Consider the following program. We can represent the executable statements in the graphical form. After counting the total number of executable statements, it is observed that the time complexity of this program is O of a function of n. The maximum degree of n in this function n is 3. Hence, the time complexity is O of n cubed. So, in this way, the performance of the software is decided by its space and time complexity. Note that if software must execute in less time, then it requires more space and vice versa. So there is a trade-off between space and time complexity. So friends, now we are ready to get started with various data structures in the next sessions.